You know that feeling, right? As a developer, you're deep in the code, you see a pattern, and that little voice in your head goes, hey, I can make this faster. We're all on that constant hunt for more performance. But what if one of the most common optimizations we reach for is actually a trap?
So let's talk about Ethan. He's a junior dev, and he's noticed his Go app is passing around these big data structures by value. Now, what does that mean? It means the program is making copies over and over again. His thinking is pretty straightforward. Making copies is slow. Passing a pointer, that's just a tiny little memory address. It should be way, way faster. And you know what? On the surface, he's totally right. It makes perfect sense.
But this is where our whole story takes a sharp turn. What if that completely logical, well-intentioned change didn't just fail to speed things up? What if it actually introduced a hidden penalty that made the whole application slower?
And that's exactly what Eleanor, a senior developer, tells him. She's like, I love the enthusiasm, but you just slowed us down. See, she understands something crucial. The real performance cost isn't about the tiny act of moving data around. It's all about where you decide to store it. And to really get why, we need to dive into the two very different worlds where our data can live inside the computer's memory.
Okay, so to really unpack what Eleanor's talking about, we have to look at how Go handles memory. Because here's the thing, not all memory is the same. There's this super fast, super organized world called the stack, and then there's the much bigger, more chaotic world of the heap. And believe me, where your data ends up makes a huge difference in performance.
So, what's the difference? Well, you can think of the stack like a neat stack of plates. Every time a function is called, it gets its own plate on top. Super organized, super fast. The heap, though, that's more like a giant, messy shared warehouse. It's way more flexible. You can store anything there for as long as you want. But it needs someone to clean it up. A janitor, or in Go's world, the garbage collector. Let's zoom in on the stack for a second. When one of your functions starts running, it gets its own little private block of memory. It throws all its local variables in there. And the very instant that function is done, poof, that entire block of memory is gone, wiped clean. It is ridiculously efficient, with absolutely zero cleanup cost. Now, the heap is a whole different beast. It's this big shared space for data that needs to stick around even after a function is over. But the catch is, there's no automatic cleanup crew. Go has to periodically pause and run this heavy-duty background process, the garbage collector, to scan through everything and figure out what to throw away. And that process, it costs CPU time. It's a performance hit. We call it the GC tax.
So the big question is, how does Go decide where to put everything? Does it just flip a coin? Nope, it's not random at all. The Go compiler has this secret weapon, a really clever process that happens before your code even runs. And this process is the key to solving our entire puzzle. By default, the Go compiler is brilliant. It's lazy in the best possible way. If you make a variable inside a function and then just return it normally, by value, the compiler knows it can just keep that thing on the superfast stack. It makes a quick little copy for whoever called the function, and the original disappears without a trace. No mess, no fuss, and most importantly, no GC tax. Just pure speed.
Okay, but this brings us right back to what Ethan did. He created a variable, but instead of returning a copy, he returned a pointer, just the memory address for that variable. So, what does the compiler do now? It's got a problem.
This is where that secret process comes in. It's called escape analysis. The compiler looks at that pointer Ethan returned and thinks, whoa, hold on. If I leave that original data on the stack, it's going to be destroyed as soon as the function ends. But this pointer will still be out there, pointing to nothing. That's a huge bug waiting to happen. So to prevent a total disaster, the compiler has no choice. It has to move the variable. It forces the data to escape from the fast stack to the slower, safer heap.
And you know what the coolest part is? This isn't some black magic happening behind the scenes. The compiler will actually tell you it's doing this. You can run your build with a special little flag, -gc flags equals mum, and it'll spit out a report telling you exactly which of your variables it had to move to the heap. It's like looking under the hood. And right there, in that output, is the smoking gun. This is the direct result of Ethan's optimization. The compiler literally tells you, moved to heap, P. That's it. His attempt to save a tiny, almost free copy operation ended up triggering a much, much more expensive allocation on the heap.
And that gets us to the heart of the matter. Ethan saved a microscopic fraction of a nanosecond by not making a copy, But in exchange, he forced a heap allocation and put more work on the garbage collector's plate. As Eleanor put it, he traded pennies for a tax bill, and it was a terrible trade.
All right, so this all leads to a really important question. If using pointers for these little micro-optimizations is such a trap, when are we supposed to use them? Well, there's a really simple, really powerful rule of thumb that separates good Go code from great Go code. And the rule is this: use pointers for semantics, not for micro-optimizations. What does that mean? It means you should use a pointer when you actually need to share state, when you want a function to be able to change the original piece of data. But if you're just passing data around, especially for small to medium-sized structs, just pass it by value. Let Go make the copy, because copying something on the stack is almost always cheaper than paying that garbage collector tax on the heap.
Ethan finally has that aha moment, and he boils it down to a perfect, simple mantra. Pointers are for sharing, values are for speed. Seriously, that's a fantastic mental model to keep in your head. Ask yourself, am I trying to share and change this thing? Use a pointer. Am I just sending data somewhere? Use a value.
And that brings us to Eleanor's final piece of wisdom, which is so important. Trust the compiler. Modern compilers, especially Go's, are incredibly smart. Before you jump in to try and outsmart it with some clever little optimization, take a step back and make sure you really understand the whole picture. Because 9 times out of 10, the real path to performance is working with the language, not against it.
So, as we finish up here, I want to leave you with a question to think about. What other common sense optimizations might be lurking in your own code that are secretly slowing you down? This whole story of the stack versus the heap is just a great reminder that in the world of software development, the fastest path, well, it's not always the one that looks the straightest.